So there's this bet, a logical bet with values 0 and 1, and he's feeling a little bit sad. So he goes to a therapist, and therapist asks him, "How much sad are you feeling?" And he goes, "Only a bit." And then therapist asks him, "Why are you feeling sad?" And he goes, "I'm only a bit, that's why." And then the therapist asks him, "Okay, so how did this happen?" And he said, "It happened bit by bit." So therapist goes like, "Okay, there's nothing to worry. Just keep doing your bet." And that's my bet, guys. So this is one more episode of Coding Interview Weekly. If you are thinking what this is all about, you can just go to lalitkundu.com, and there's a brief introduction there as well as the problems from previous weeks. Pardon my handwriting. So let's jump into the problem for this time. And let's say I wanna, okay, let me iterate through the problem, what this is about. Basically, in this problem, you are going to design a key value data structure, a map-like data structure, which can support these operations. And for for the initial version, let's start with this, where you have to increment a key by value 1, and you have to decrement a key by 1, and then you just have to output the key with the maximum value. So let's try this version first because the other one is slightly more complicated. This is what I would typically start an interview with. Uh, I think I really like this problem because it not only explores the fundamentals, but as well as the candidate's understanding of some of the inbuilt data structures that various programming languages provide. So I think any candidate would be aware of a map, which is basically a structure which maintains pairs of keys and values, and it can support increment decrement operations simply, depending on the underlying data structure, like whether you're using a search tree or hashing, you'll get corresponding time complexities of these operations. So in a search tree based implementation, we know that the keys are ordered basically, right? So keys are ordered. Whereas in a hash map implementation, a hashing based implementation, we know that there's no ordering of keys. In this case, however, we are trying to order the structure by values because we're trying to find the key with the maximum frequency. And a candidate can typically go in a few directions when they're thinking about this. One of them is, okay, I have a search tree which is ordered by keys. Maybe somehow I can also maintain ordering of values as well. Uh, I think this is a much more complicated approach, and maybe we can use an auxiliary data structure to store the same information, but in a different format and use that. So we know that we have a data structure like map, which maintains an ordered set of keys. And we are trying to find an ordered set of, we are trying to maintain an ordering of values. So why don't we define another hash map where we'll store values as keys and keys as values? Basically, let's call this one M1, this is M1, and this is M2. So M2 is basically a reverse map of M1. And in this case, we know that M2 will order the values in an increasing, order these values in increasing order, and hence we can just output the last element of M2 to find our answer. And that's a pretty good solution. It works really well. And in terms of time complexity, you should think about it. M1 these does not need to be ordered as such. So we can do order one operations, increment and decrement. But when we try to reflect them in M2, we need to uh, remove an element from the keys. Basically, if the value of key K1 is changing from V1 to V2, we need to remove K1 V1 from M2 and insert K1 V2, and that's order of log of size of the container, which could be the total number of operations that have happened till now. And hence we get an order log n for query number 3 and constant time operations. Actually, not constant time. It's order log n for operation 1 and 2, whereas constant time for operation 3, which is output the key with the maximum value. In a good interview, I think I would expect the candidate to come up with this within 5 to 6 minutes, because this is nothing but just using some of the inbuilt data structures, and you're just changing how you represent your data, and that itself is helping you solve some of the queries efficiently. And this is a great skill to have. Actually, this is what we're looking for in interviews. So typically the next thing to do would be, let's try to improve these login operations somehow. And this is where the problem gets really interesting. So what is the crux? What is the crux of this problem? Like, what's the fundamental observation here is gonna be this. Let me erase some of this stuff. So I'm gonna represent values by frequencies now. That's basically easier to deal with when talking about this stuff. So you have keys, and each key has a frequency. Let's say the highest frequency, which is basically what our answer is F right now. And let's say we perform an operation. What can really happen to F? So there are a few cases that can happen. One of them is, before that, let's try to represent things in a different way. Let's say you have this number line, and these are your frequencies. And corresponding to each of the frequencies, you have a list of keys that correspond to that frequency, right? And you can have multiple of those. So we are saying right now the highest frequency is F. What are the possible things that can happen? The first thing that can happen is frequency F remains, the highest frequency remains same. And when does that happen? Basically, we are changing the frequency of an element, which is not here, So one of the elements moves from 1 to 2, let's say, and it gets erased from here. This does not affect F. Okay, what else could happen? The other thing that can happen is the highest frequency increases by 1. And when does that happen? That happens when we take one element from here and increments its frequency. So it ends up creating an even higher frequency, right? What else could happen? There's one more possibility, which is that the highest frequency reduces by 1. And the scenario in which that would happen is, let's say these operations have already happened and F plus 1 is the maximum frequency. We perform a decrement operation corresponding to this element, and that would basically move it here, right? And the highest frequency would now be F. These are the only 3 possible scenarios that can happen when you increment or decrement a corresponding key. So how do we identify, well, if we have a way of identifying these scenarios, like either we incrementing one of these or one of these, or let's say one of these, we can simply figure out what's the new answer gonna be and just keep maintaining the new answer along the way. And that's very straightforward, right? Corresponding to each of the frequencies, you maintain a list of elements that have that frequency. And if you are incrementing a key, you just have to remove an element from that list and move it to a different list corresponding to the next frequency or the previous frequency. So we need a new data structure here. We are looking for a list-like data structure in which you can add an element, you can remove an element, and you need to, let's say, output any. Okay, Great. And you need to output any of the element in this list. Let's say we're going to do that. Uh, what does, I think it's pretty easy to come up with that. It's a simple set, right? It's an unordered set. It's just a hash map. You can use a hash map. You can use a unordered set. Basically, all of these approaches are hashing based, and that should give us a constant time for all three of these, right? Okay, what is going on? Yeah, so all of these can be done in constant time. And that basically enables us to do all the operations in the original problem in constant time as well. And at this point of time, I think a typical candidate that would get hired would take around 20 minutes to come up with this algorithm. And this is really good, I would say. If you can implement this without any bugs, you certainly get a higher rating from me and like usual interviewers at Google as well. But if you are really, really fast and we still have some more time to discuss, I would jump into the much more complex part of this problem. And that's the next part where we talk about uh, supporting another operation, which is you have to output the key with the minimum value as well, right? And this is where things get a lot of fun. So this was for max. Let's talk about min now. Okay, let's try to extend the same solution, the same approach. How would we do that? Let's say the lowest frequency right now is f. What can possibly happen to f when we increment or decrement a key? If we are decrementing a key, like f will go to f minus 1, right? That's for sure. So that's great. We can go to f minus 1. But if we are incrementing a key, that means, let's say this is the minimum one, right? Let's say this is f right now. This is f right now. And we are going to increment this by 1. We are going to increment the frequency of this element by 1, right? And that would increment f by 1, so we can go to f plus 1 as well. What else can happen? Let's say we decrement the key with the minimum frequency right now. Now this is where things get tricky a little bit. What could happen is let's say you didn't have all of this in between. So what you did was you decremented the key with this frequency. So it's gone now, right? What happens to f? F can arbitrarily change to f plus k. And this is what the tricky part is. How do you know which is the next possible frequency, which is the next minimum available frequency, which you can, which is basically a new answer. And that's why we need a slightly more complicated approach. Like we can't keep a running answer in this case. Because if we try to iterate over f plus 1, f plus 2, f plus till f plus k, in the worst case, we may actually end up traversing up till order of size of the container in the worst case. So what comes to your mind? I think typically what we can do is if we were magically able to maintain a pointer to each of these next possible frequencies, we can just essentially go back to that, go to that node, go to that frequency where f would be pointing, And that would be our answer right now. But this is slightly more complicated. So let's try to simulate. This is the direction you want to go in. So you need to communicate the direction that you're going into the interviewer. Say that this is what I'm thinking about. This is obviously not in final form. So I'm gonna weed out some of the details by trying to simulate these operations, like increment a key and see what are the possible things that can happen. Okay, so let's try to see what are the cases that can happen. Mm, so one case we have already described where a certain frequency gets deleted, right? What if this node was in between? What if this node was getting deleted? We need to update this previous node's pointer to point here, right? That is what we need to do because this node is going away. This one is being deleted because there's no corresponding key for this frequency, which means how do we know what is the previous node? How do we know which node was pointing to this node? Which node was pointing to this node? For that, we just need to look back and have another pointer. Essentially, this becomes a doubly linked list because we're going to try to delete some nodes from in between, and it's easier that way. Okay, this does not look very great, but you get the gist. Like it's a doubly linked list. Every node is connected to its forward node as well as backward node. Okay, now let's say this node is getting deleted. You have to readjust the pointers such that your list is essentially still connected and not, becomes a forest. What else can happen? The other things that can happen are one of the elements, let's say this element, is changing its frequency. So there, let's say if we increment it, it can go to f plus 1. It can also go to f minus 1. If the node with frequency f plus 1 does not exist, we need to create it. Similarly, if the node with frequency f minus 1 does not exist, we need to create that. And all of these, note that all of these operations are constant time because we are essentially pointing, we are creating a node and we are changing the pointers. So we are not traversing in any of the directions. So this is the best possible solution for this problem, which does all operations in constant time, all of them, right? If you have to find the key with maximum value, you can just look at the last node. For the key with the minimum value, you can look at the first node. So that's the really beautiful problem that we have discussed today. In terms of implementation, I think the linked list approach is very complicated to implement. If you're going to go with primitives, right? Like actually defining a struct yourself, creating the pointers, deleting them, and so on, that is much more complicated. In C++, however, you can use the list container, right? You can use a list. And in list, you can maintain pointers. So we'll have a map of frequency to an iterator. Let's just call it iter. Yeah, to an iterator which points to elements in this list, right? And once we have that, once we find the iterators, it's very easy to reference to the previous iterator, which is basically the previous node, as well as the next one in constant time. You can delete iterators. You can delete the element to which the iterator is pointing to. Also note that if we are deleting iterators, it should not affect the map basically because the iterators they'll adjust themselves because it's the same memory location at which the pointer is pointing to. So that should not matter. We don't have to readjust all the iterators in the map. And that would typically be an easier way to implement it. Otherwise, I'm sure it'll be very hard for me to debug as well, to point out issues in your code. Yeah, and if somebody implements this, that's a strong higher rating, really. I don't think I would not have been able to do that for sure in an interview. What else? I think this is it for this week. Go check out lalitkundu.com. I'm gonna post some more problems like these data structure problems that you can try to solve. And there's this really fun thing that I want to tell you about implementation. So folks would implement something, and then I typically would ask them, "Oh, so you think this is ready to go? Like, you think this is ready? There are no bugs in this." This is basically a final warning that if you think there are some bugs, you should fix them, and they won't discount your performance. And folks would typically start dry running their code on some sample input, right? And then I tell them, okay, you are not allowed to dry run anything. You just have to read the code and find an issue with it if you can do that. Uh, Either you do that or you're really fast at mental computation and you're still dry running and you're not showing that to me. It's fine either way. But I believe if you read through the code, you can figure out the invariants that you expect to be true always. The risk with dry running is you're you are as good as the test case that you have chosen. Whereas if you are reading through the code, you are evaluating all the corner cases in your mind and all the invariants that needs to be maintained. So that typically is how I read code as well in interviews as well as in real life software engineering as well. So that would be my advice to all the folks who are trying to implement stuff in interviews. Yeah, this is it. Feel free to leave any comments, follow-up questions, and I would be happy to answer those. See you next week.